Welcome back to Data Science Live. In part 2 of our Algorithm Explainer, we're cutting the fluff and getting straight to the core of how data science systems are actually built, tested, and where they fail. So let's jump right into the most fundamental question about any model.
So, you might be wondering, before an algorithm is unleashed on the world, how do the creators actually know its mathematical predictions are right? Like, how is that accuracy tangibly proven? Well, here's the secret. Data scientists never, ever test an algorithm using the exact same data it just learned from. Instead, they use what's called a train test split. Imagine they train the algorithm on a massive vault of, say, 8,000 labeled photos. But they keep a totally separate batch of 2,000 brand new photos locked away in a hidden testing vault. Once the training is done, they finally unlock that vault and show those 2,000 hidden photos to the algorithm. If it correctly identifies 1,900 of them, boom, that's your mathematical proof. The model has a 95% accuracy rate on real-world data that it has absolutely never laid eyes on before. Okay, but that brings up a really valid beginner question. If an algorithm is mathematically proven to be 95% accurate, why on earth do we constantly see headlines about machines acting unfairly or giving totally biased results? It all comes down to algorithmic bias. Look, algorithms don't have personal opinions. They don't hold prejudices. They are literally just mirrors. So if the historical data we feed them is packed with human biases or systemic flaws, the algorithm just absorbs those toxic patterns and projects them right into the future. To put that into perspective, let's look at Amazon's former recruitment algorithm. It was trained on historical hiring data, but because the tech industry had historically hired mostly men, the algorithm mathematically concluded that being female was a negative factor for success. Crazy, right? It literally penalized resumes that included the word women's, like women's chess club captain. The math worked perfectly, but the historical data was deeply biased. Now, creating systems that complex probably sounds incredibly intimidating. You might assume that building these models requires a whiteboard completely covered in terrifying calculus equations and writing code from absolute scratch every single day.
Actually, scratch that. It's not like that at all. Modern tools have totally abstracted the heavy math away. You write in Python, which honestly reads pretty close to plain English, and you use a Jupyter Notebook, which is basically the data scientist's version of Microsoft Word. It's kind of like driving a car. You don't need a PhD in thermodynamics to drive to the grocery store, right? You just use the dashboard and the pedals. In data science, you just pull pre-built world-class models from libraries straight into your notebook and hit run.
Because these tools are so incredibly accessible now, development is happening at a massive scale, which naturally raises a critical question. With all these algorithms being built so easily, who is actually acting as the safeguard? Who ensures they are safe, ethical, and fair? Well, an entire ecosystem has grown specifically to police this stuff. Today, rolling out a model relies heavily on AI ethics boards, data governance teams, compliance officers, and really strict government regulations like Europe's AI Act. Their entire job, the whole shebang, is to audit these models for bias and privacy before they ever reach you and me. In practice, this means before a credit card company lets a loan approval algorithm go live, their governance team will aggressively stress test it. They'll simulate thousands of fake applicants from all different zip codes, income brackets, and backgrounds. They do this to mathematically prove the system treats everyone equally before pulling the trigger. But hey, even with perfect governance and completely ethical data, models can still fail purely on a mathematical level. And this usually happens in two very distinct, very frustrating ways: overfitting and underfitting. These are literal nightmares for data scientists. Think of overfitting like a student who memorizes a practice exam perfectly, gets 100%, but then totally bombs the real test because they didn't actually learn the underlying concepts. They just memorized the noise. Underfitting is the exact opposite. The algorithm is just way too simple to find any meaningful patterns at all. It's like trying to predict a house's market price using absolutely nothing but the color of its front door. Both of these situations guarantee a completely failed prediction. When these models actually are tuned correctly, though, the results are incredibly powerful, and you experience them literally every single day. Think about it. How exactly do social media algorithms know what you want to watch before you even type it into the search bar? They use a fascinating system called collaborative filtering. Step 1, the algorithm tracks your micro behaviors, like lingering on a video for just a few extra milliseconds. Step 2, it maps your behavior against millions of other users to find your exact matches, your profile twins. Finally, step 3, it recommends unseen content based on what your matches liked. So if you and another user both watch coding videos and your twin suddenly likes a hiking video, boom, the algorithm instantly pushes that hiking video to your feed. This level of extreme profiling leads us to the absolute most complex and, honestly, the most concerning type of system in modern data science, the black box algorithm. So, what exactly is a black box, and why does it have so many people worried? A black box algorithm is a highly advanced model, like a deep neural network. The catch is that its internal mathematical calculations are so massive and so intricate that even the engineers who built the thing cannot trace exactly how it made a specific decision. You see the data go in, and you see the prediction come out, but that entire decision-making process in the middle, it remains a complete, untraceable, dark mystery. Imagine a medical AI that looks at an X-ray and is 99% accurate at flagging a tumor. Sounds great, right? But when a doctor asks the AI, hey, which exact pixels made you think this is a tumor? The AI literally cannot explain its reasoning. This total lack of transparency makes black box algorithms incredibly risky for high-stakes fields like medicine or criminal justice. So it leaves us with a pretty heavy question. If a black box algorithm is 99% accurate, but completely incapable of explaining its reasoning, should we really trust it with human lives? Is sheer mathematical accuracy ever truly enough if we can't understand the fundamental logic behind the machine's most critical decisions?